Okay, hello everyone. Thanks for coming. My name is Philipp Burckhardt, and I'm a PhD student at Carnegie Mellon University. And today I'm going to speak about real-time machine learning using Node, which is kind of an unusual combination, actually. So why is that? I guess just because of tradition. Mostly people in statistics, my field, have used like this programming language called R, whereas programmers from computer science, who do machine learning work, mostly use Python. And so the advantages of using Node and JavaScript are kind of overlooked that way. But there are actually quite a few of them. And so there's no reason why we can't do all machine learning tasks also with Node. And so that really was one of the main reasons why I teamed up with Ethan Reens, whom you might have known by his talk on math in V8 and why it's broken and how to fix it previously today. And we teamed up and built and tried to fill the gap by building the standard lib library by bringing numerical computing, statistics, and machine learning more into Node. And so having said that, no more introductions. What is machine learning? So I like to think about it as the study of how to learn patterns from data. Okay, so imagine that you have some predictions that you want to make, or you want to investigate the relationships between different types of variables. So in these situations, machine learning can help us to separate the signal from the noise and being able to make sense of the world in a way. And here, really, this is a high-level description, but bear with me. In a few minutes, we will talk about the different types of problems that we can answer using machine learning methods, and those are actually pretty limited in scope. So it's actually not that big of a field in a sense. So, but first, we call that the title of this talk starts with real time. And let me spend a bit of time talking about that. So, right, in the past, when people say in statistics and had to analyze data, they always worked with static data sets. So you ran an experiment, or you collected data, and then you applied some methods in order to learn from that data. But this is really different nowadays, right, in the internet age, where we have data coming in as a data stream. So if you run a website and have a web shop, then customers come in continuously on a continuous basis. And so that kind of should maybe also be reflected in the methods of how we work with this. But in the past, like most methods that are used for machine learning or for doing statistics, they are what I would call like batch algorithms. So what you do is you build a model that can make predictions on new data, but you build this model using all the available data that you have. And if you were to obtain new data points, then what you would need to do is you would actually kind of retrain your entire model using the new data. And then you can imagine that this really doesn't scale well, right? So if you have like a big, especially nowadays where we have big data sets, then one might need to think about different ways about how to do these things. And there are some incremental algorithms which can come to the rescue here, which basically allow us to update our models as new observations come in. And so how could some of this look like? So let's take probably the most simple example that we can think of. So here it's just about estimating, like, let's say, the sample mean, so the average of a number of observations, which might actually be a good prediction if you don't know anything else about the observation. So let's imagine we have, say, you have a customer coming to your shop, right? You want to estimate how much money is he going to spend. So if you don't know anything else about this customer, maybe the average of what people spend on your page might be a good guess. So let's look at some code about how we can do this. So first here I load two of the modules that we have developed. The first is just a uniform random number generator. Second one allows us to calculate the mean in such an incremental fashion. And then the API looks like this. So we first get this accumulator object back if we call the function the first time. And then this accumulator kind of is an object which holds the current estimate of the mean. And then for each new data point that we get, we basically can update this accumulator by just passing in the new values. And if we want to retrieve the current estimate of the mean, then we just call the function without any arguments at the end. So this is kind of similar like a reduce operation, right? If you would just reduce and then pass in kind of a plus b as the callback. So now prediction is in general a very difficult task. And as this quote of Niels Bohr reminds us, this is especially true if we are making predictions about the future. And why is that? Just because the past is not always indicative of the future, right? So just recall the financial crisis of 2008, where all the banks had these complicated financial models, right, trying to predict risk, but they didn't see that coming, that one coming, just because maybe some underlying systematic relationships in the system changed. And so on a more basic level, many machine learning algorithms actually are based on this assumption that data is independently identically distributed, which is clearly not the case if you, so there are many violations of this, but let's first parse what this means. So independent, you can just say picture like a succession of coin flips, and basically a coin has no memory, right? So every successive coin flip does not depend on what came before, so that then the coin flips are independent. And identically distributed in that context just means that each coin flip, kind of the process which generated each coin flip, must be the same. So in that case, if you have a fair coin, let's say, you flip it, the probability of getting heads should be 50%, and it should stay that way over all the coin flips that you have. So as we said, these assumptions are often violated. So for example, in time series, you don't have that, usually because you have trends, right? You have trends that, so today's values depend on the past, etc. And so in technical terms, this is called non-stationarity. But even like beyond that, there's just this fundamental problem that if we use data to make predictions and our system changes, then we are kind of out at our wits' end, right? So there are definitely these limitations also that where machine learning then cannot really help us. But let's look at a simple example of how we can use where we have maybe not IID data. And what we want to do here is we want to not calculate the mean, but the moving average. So this is kind of analogous to the first example, but here we calculate a moving average. So the moving average calculates the mean, not taking all the observation into account, but only like a window size. So we have to specify a window size of say n, and then only the n last observations will be used to estimate the mean. And in this example, let's say we want to look at the amount of free memory that we have on my operating system. And so I will load this incremental moving mean function now, and then I also load the native OS module just to get the free memory. The API is pretty similar, except when we initialize this accumulator object, now we also pass in like the window size. I just chose 5 here. And then let's maybe check each second what's the currently available free memory, and then we update the accumulator, passing in the current free memory, and then we can get the current estimate of the mean out by calling the function without supplying any arguments. Okay, so how could this look like? So here, what you can see here is the red line are the original data points, and then the blue or cyan line here, those are the moving averages. And one thing we can try out here, like if, for example, if I change the window size to 33, what you will see here is now that we get a smooth line. So we smooth out all these little differences and all these irregularities and spikes. And that can be useful on its own, basically, because like if you are doing any type of data visualization of time series, it can often be useful to look at moving averages to get a better sense of the underlying trends. And so that's one application where it might also be of use. Now, these were kind of two very simple examples, right, of doing statistics. But now there are many different types of machine learning algorithms that one can use, right? So you have support vector machines, there are decision trees, random forests. We just heard a great talk about how to use neural networks to learn games. So there are all these different types of algorithms, but then it can be quite easy to kind of miss the forest for the trees. So what I would like to do now is talk a bit about the different types of problems that we can answer with machine learning, because these are actually pretty limited in scope. And so that, I think, is the better way to approach this. And the first of these problems is kind of called regression, right? So in a regression problem, basically what you want to do is you have a numeric outcome that you want to predict. And you have one or more explanatory variables or variables that might drive this outcome. So let's look at an example for maybe housing prices, okay? House prices. So these depend on like different variables that you can think of, right? Depends on the size of the house, the number of bedrooms, like how's the neighborhood like, etc. And so now, for example, on the left plot there, you could imagine like maybe on the x-axis we actually have one of those variables which influences the house price, and then the y-axis we would have the outcome variable, which would be the price. And then basically regression just boils down to kind of fitting a curve which goes best through all these data points, right? Or which minimizes some error and goes through these 8 data points. And you can do this also in multiple dimensions, right? So we obviously have more complicated settings where we have many high-dimensional problems, but then we cannot visualize it, right? We cannot go beyond 3 dimensions of visualization, but the principle is the same. So that's regression. And then there's classification. And in classification, what we want to do is we want to predict group memberships. So you have different categorical outcomes, so different categories that you want to predict. So let's take a look at the plot here. What you can see here is that we have 3 groups. We have the green, the blue, and the orange ones. And we have 2 variables on the x and the y-axis, right? So 2 explanatory variables. And we can see, for example, that it seems that on the y-axis, if we are below some threshold, maybe 40 or something, then it's pretty clear that we will have an orange variable or observation, versus above that, it really depends on the variable on the x-axis, whether we are in the blue or green category. So then what a classification algorithm will do, it will help us to find the decision boundary, which helps us to classify like new observations into any of these 3 groups, right? And one example for this could be, let's say, optical character recognition. So imagine like in a post office where you might want to, you have letters on an envelope, right? And you want to, like handwritten characters, and you want to detect like what of the 26 letters of the alphabet does this stand for, okay? And the third and last type of problem is clustering. In clustering, we also want to detect groups. So one might think it's pretty similar to classification, but it's actually the opposite. It's very different. And why is that? It's because we don't know what the groups are, okay? So you can imagine, as in the right plot here, you just have these gray data points, and now you want to find out how could you separate these points into different groups such that the elements in a group that are assigned to a group are similar to each other, but are different to the observations that are assigned to the other groups, okay? And maybe an example could be like, I have here as an example, movie tastes, right? If you're running a recommendation service and you want to show people like what movies they might enjoy based on their past history or from what movies they watched and liked, that would be a typical clustering application. So now, before wrapping up, what I would like to do is go through 2 examples for both regression and classification, and then also provide you to some further point you to some further resources that you might want to check out. So again, regression, let's remember it was if we want to model the relationship between a numeric outcome and one or more explanatory variables. And let's say, to look at a simple example, I thought, okay, maybe we would like to predict the number of package versions that a module on NPM has. And yeah, the most obvious, I think, predictor I could think of was age, right? So how old the package is. So a reasonable suggestion might be the older a package, maybe the more versions it has on NPM. So let's look at this example. What we do here is we first hook into we use this package stream module, which allows us to hook into the CouchDB database of the NPM registry, and then since a certain date. And then we also load this online regression module, which kind of, it's online SGD regression. SGD is kind of the algorithm used. It's a stochastic gradient descent algorithm. And then we have to initialize this model here, where we supply some parameters. So I don't have enough time to go into details here, but you might want to read up on that if you're interested. And then what we basically will do here is we look for these package changes. And so when we get one, what we do is we get the number of versions the package has, And then we also get its age, so we need to, in years, so I need to do some transformations here. And then let's update our model using, by supplying basically the vector of explanatory variables. Here we have only one, age. And then as a second parameter to the update method, we supply the number of versions. So how does this look like? So you can see here now, you get these new data points, these incoming data points. On the x-axis, we have the age. On the y-axis, we have the number of versions. And you see like how the regression lines updates as new data comes in, okay? And you see it's still pretty erratic, right? So that it's fluctuating widely. And that's just because like we need to run this over many more iterations, right, until this will converge. But what you might have already seen, there is a clear positive association, right? And so you might end up with some regression equation at the end. So in this case here, we see if this was the truth, right, which it isn't, but maybe like if a package would be 1 year older, right, you would expect it to be kind of have 6 more versions on NPM, or 6.8 versions on NPM, right? Something like that. And so that was the regression problem. Let's look at a classification example. Here, remember what we want to do is we want to model the relationship between a categorical variable, so we have multiple categories, and we have one or more explanatory variables. And here, I would like to restrict ourselves to like the binary outcome. So just imagine you have 2 outcomes, right? And I was interested in looking at what kind of packages do React.js packages depend on. So, I mean, React is a hugely popular Facebook framework for developing user interfaces. And I was interested in different build systems, different testing frameworks. So what's kind of popular in React packages. So let's look at this. Again, we hook into the CouchDB database. And then now I load this online classification module, which has a similar API as the regression module we've seen before. So again, create a new model. And then as the new data points come in, what we will do is we first create this outcome, which is where the package uses React, where we just define this as, okay, does the package JSON file contain the keyword React or not, okay? So that's it. And then this is kind of a toy model, but let's just look at maybe 5 features. Let's look at whether the package uses Webpack, depends on Webpack, or depends on Browserify for bundling, and I considered 3 testing frameworks here, so Jest, Tape, and Mocha. And then what we can do is we can get predictions out of our model using this predict method, where we supply like the features, and we specify here that we want probability. And then if the probability is greater than 0.5, we say, okay, we make a new prediction. The prediction will be, okay, this uses React and otherwise not, which is the -1 stands for, right? And then we also update our model using the data here. So how does this look like? So here what you can see is on the left side, you get all these new packages coming in, and they're green if we get them right, red otherwise. And on the right-hand side, you have this matrix that's called a confusion matrix, where you see the correct classified observations and also like the false negatives, where we predict no, but in reality they use React, and we also see the false positives here. So, so you need to, again, run this for a long time, ideally, which we don't have time for, but let's just look what we get so far. So in this bar chart on the bottom right, you see kind of the variable importances. So, and what you will end up seeing is that Webpack seems to be pretty indicative of being a React package. So that's, I guess, to be expected because Facebook uses Webpack in its own examples compared to Browserify. And in terms of the testing frameworks, Mocha doesn't really seem to be associated very much with React packages. I guess Mocha is just so popular in general in the Node ecosystem, so many packages use it, and that's likely the reason for that. Yeah, so that's the classification example. So now, how do you evaluate the quality of these methods? So what you want to do is you want to look at the generalization error, and that's the performance of your model on data that has not been used for training your model, okay? And if we look at this toy model we just developed, what we will find is that it has a misclassification rate of 13%. And that might not sound too bad, but actually, like if you, in this case, like only 15% of the packages nowadays on NPM use React. So, like, you would just get 15% misclassification rate if you were always to predict that it does not use React. So I guess one could do better if one did a proper search for what variables to use. OK, so I need to quickly wrap up. Clustering, again, right, was when we want to group observations into meaningful clusters. And there are different algorithms you might have come across, such as k-means, db-scan, hierarchical clustering, statistical methods like mixture of Gaussians, etc. So if you want to learn more about those, I would suggest 2 free textbooks by Stanford professors that you can download from their websites, and there are also accompanying video lectures. The first one, an introduction to statistical learning, and the second one, which is a bit more advanced, it's called The Elements of Statistical Learning, Data Mining, Inference, and Prediction. And here's also like, OK, that's not displayed correctly, but anyway, so that's the link to the repository of the standard lib library. It's still pretty much in development, but we would be happy to get some feedback. And so, yeah, check it out if you're interested. And there are also some stickers here if you want, you can grab them. And with that, I would like to thank you. Yeah, thanks for the attention. And enjoy the rest of the conference.